All right. So yeah, just a reminder, homework's due on Wednesday. I have office hours today at 4 and then again tomorrow at 11. On Friday, we started or sort of continued talking through matched asymptotic expansion methods. And we found that for our example problem, that the following boundary value problem has a boundary layer on the left such that we can match this left-hand boundary. And here at x equals 1, we have no boundary layer, at least to our first order expansion. Our outer layer solution we found to be of this form, and our inner layer solution, which we matched to that, was of the form YL is equal to ALO plus BLO e to the minus x over epsilon. And this inner layer here gives us these compressed coordinates that allow for this rapid change to happen in the solution, such that we match that boundary condition. Now, the last thing we kind of talked about, right, is when you construct the solution, right, after getting the outer and inner layer solutions, okay, you're going to essentially sum them to get the composite solution, okay, but they subtract the common part, okay? And what we found was our common part in this was this constant EB here, okay? Which is the limiting value that you get at the right side of the inner layer and the left side of the outer layer, okay? So this is our common part here, okay? This is our inner solution, and this is our outer solution, okay? So that's a general idea of pretty much all matched asymptotic methods. We're going to look at a few different situations over the next couple days. I just wanted to kind of briefly go through how you would go to higher order in this problem. I don't want to spend a lot of time on it because I want to get over to other examples of matching, okay? But let's say that we wanted to look at higher order terms for our problem here, okay? And so in this case, we're going to look to order epsilon in each region, okay? And I'll just use this notation that now our left-hand boundary is going to have an inner solution given by EBXL plus A minus EBXL e to the minus XL plus AL1 plus BL1 e to the minus XL. Where remember XL was our stretch coordinate, or sorry, our compressed coordinate here, X over epsilon. Our outer solution is going to be of the form minus EBX times e to the minus X plus AM1 e to the minus X, okay? And our right-hand solution is going to be minus BXRA R1 plus B R1 e to the minus XR, okay? And our boundary conditions are going to give that AL1 plus BL1 equals 0, A R1 plus B R1 is equal to 0, okay? So that's looking up here at these boundary conditions, right? There's no order epsilon terms. So our left and right hand boundaries are 0, okay? The way we would get these solutions, okay, and then show all the intermediate steps, but we just go up to order epsilon, right, in our different hierarchy of differential equations that we derive, okay? We wrote those down on Friday, okay? So we just solved those. They're linear differential equations. We get these, exponential solutions to them, okay? So now that we have these, right, we have some free constants, right? We have free constants sort of in the homogeneous part of our solutions here. We would follow the same procedure to match. Okay, and so on the left, you get this longish expression YL is equal to EB plus A minus EB e to the minus epsilon alpha minus 1 x hat, okay, for some intermediate scaling, epsilon minus EB epsilon to the alpha minus 1 x hat now, okay, plus A minus EB epsilon to the alpha minus 1 x hat times e to the minus epsilon to the alpha minus 1 x hat, okay, plus AL1 plus BL1 e to the minus epsilon alpha minus 1 x hat, okay, plus higher order terms, order epsilon squared. So this implies that YL is going to be given by EB plus some exponentially small terms minus EB epsilon to the alpha x hat plus AL1 epsilon plus some exponentially small terms plus order epsilon squared, okay? So that's what happens as we go to the right-hand side, or we go to the right of our left-hand inner solution, right? And remember here we're in our inner solution and we're going this direction. Now we also have to look at our outer solution coming in. And we need those to match up, okay? So in this case, ym is going to equal EB e to the minus epsilon alpha x hat plus epsilon minus EB epsilon to the alpha x hat e to the minus epsilon to the alpha x hat plus am1 e to the minus epsilon to the alpha x hat plus order epsilon squared, which is asymptotically epsilon to the alpha x hat EB. We just expand that exponential, epsilon to the 2 alpha x hat squared divided by 2 EB plus some higher order terms minus EB epsilon to the alpha plus 1 x hat minus EB epsilon to the 2 alpha plus 1 x hat squared plus am1 epsilon minus am1 epsilon to the 1 plus alpha x hat all the way up to order epsilon squared terms. Okay. So if we match these terms, at the end of the day, we find that AL1 is equal to AM1, okay? And we also need that alpha equals a half, greater than a half, okay? So our neglected terms are smaller than epsilon, okay? Now, on the right, we can do something similar, again, in order to get this matching. I'm not going to write all that out, but essentially what we find if we do something similar, we take an intermediate coordinate, right? We go to the right with our outer solution, and then we go back to the left with our inner solution from the right, okay? We get that BR1 is equal to 0, AM1 e to the minus 1 minus b equals AR1, okay? So in total, we have that AR1 equals 0, BR1 equals 0, A, M1 equals BE, AL1 equals BE, BL1 equals minus BE. Okay, so YL1 equals minus EB XL plus A minus EB XL e to the minus XL EB minus EB e to the minus XL. And Ym is equal to minus EB x e to the minus x plus EB e to the minus x. And YR1 is equal to minus B XR. Okay. So we can create our composite expansion, okay? And if we identify the overlap, okay, of YL and YM, okay, what we find is that YL now is equal to EB plus A minus EB e to the minus x over epsilon plus epsilon minus EB x over epsilon plus A minus EB x over epsilon e to the minus x over epsilon plus EB minus EB e to the minus x over epsilon, so on, okay? And asymptotically, this is going to give us EB minus EBX plus epsilon EB plus order epsilon squared terms, okay, in our outer layer. If we add our left and our middle solutions together, the so the YM solution is going to be EB e to the minus epsilon XL plus epsilon minus EB XL e to the minus epsilon XL plus EB e to the minus epsilon XL, if we write it in terms of the inner coordinates, okay? And it's also going to have that same term showing up, okay? YM is going to have EB minus EB epsilon XL plus epsilon EB plus order epsilon squared, okay? So we essentially need to remove this whole term once, okay? And at the end of the day, if we then sum our left and middle solutions together, we get A minus EB, epsilon B, e to the minus x over epsilon, plus A minus epsilon B, x e to the minus x over epsilon, minus epsilon EB e to the minus x over epsilon, plus EB e to the minus x, minus epsilon EB x e to the minus x, plus epsilon EB e to the minus x, plus order epsilon squared terms, okay? So just to sum up, at higher order, the idea is the same, okay? You're just going to get longer and longer expressions each time you go up the hierarchy. So typically, you stop at leading order for these problems, because that's usually good enough. If you start going to higher and higher and higher order, oftentimes what can happen with asymptotic expansion is that they can actually get worse if you take, 5 terms in an asymptotic expansion. So 1 or 2 terms is usually sufficient, and oftentimes you're just interested in sort of a leading order scaling. Yeah, the other thing is that these sort of matching conditions and subtracting off in order to get the composite expansions. Yeah, it can seem a little kludgy to do. You're just sort of subtracting these things off, but the resultant solution should still satisfy your differential equation up to whatever order you solved it to in that case, because you have that term where you need it both in the inner and outer solution. It's just that you're not including it twice unnecessarily. Okay.
Why, when you're doing that, do you put XL back into YM instead of just keeping both in terms of the same variable?
Yeah, you could. I mean, I just did it here in order to show that this essentially is what you're going to see in the inner layer if you take the outer solution into the inner layer. And
Okay.
then I was showing this is what the inner solution is going to look like when you take it into the outer layer, right?
Okay.
But yeah, if you want to write it down so that they're in the same coordinates, that's fine too. Right? So it was just for illustration or something.
Got it.
Okay. So what's next? So I want to do a couple more examples of matching for boundary value problems with boundary layers. And then I want to eventually get more into alternative ways that you could get these inner solutions. Okay. So for the rest of this lecture, and also into the next one, we're mostly going to still be talking about these boundary layer problems. So what's next? Let's examine a problem, okay, with boundary layers on both ends, okay? And for this problem, we're going to have a small parameter both in our highest order derivative as well as in our first derivative here. X is going to just live on the unit interval. And let's take concrete boundary conditions here. Okay. And let's start off with a regular expansion and see how that does. So y is approximately y0 plus epsilon y1, and so on. Okay. Now, what we'll see immediately, right, if we plug this in, is that at y0, we just get y0 is equal to epsilon to the x at order 1. So this should be a big area. Draw it as such. Okay. And of course, it can't address the boundaries at both ends, right? And in fact, whereas the last problem that we looked at, we could at least address the boundaries at one of the ends, right? We don't have a free coefficient here, right? So as we draw this, right, there's a boundary here that we're going to need to address, and there's a boundary condition here that we're going to need to address, right, in order to match everything up. Okay. So just like the last problem, we're going to have to construct sort of these left and right boundary solutions, okay, which are inner solutions. And so on the left, right, we want to take some scaling of our coordinates, but we don't know ahead of time what it's going to be. Okay. So if we plug this in, we get epsilon to the 2 minus 2 alpha d2yl dxl squared plus epsilon xl dyl dxl. We have an epsilon to the 1 minus alpha here, right? Yeah. 1 minus alpha minus yl, and then we have equals minus e to the minus epsilon to the alpha xl. Okay. Now we'll note that e to the epsilon to the alpha xl is approximately equal to 1 plus epsilon to the alpha XL, this expansion, okay? Now to balance, we'll take, sorry. Let's do that here. All right. We remove this additional alpha here, like with this term. So that's where that goes. Okay, sorry. So we have the following sort of powers in epsilon here, right? We have epsilon to the 2 minus 2 alpha. We have epsilon to the 0, and we have an expansion here that's going to have 1 and epsilon to the alpha, right? Okay. So to balance in the distinguishing limits, okay, we want the highest order derivative, okay, at leading order. So there's a couple reasons for that. One is that we ensure that the sort of the dominant behavior of the differential equation here is exposed in our the next order of expansion, or sort of the next correction. But also this having higher order derivatives in our equation allows us to get these sort of smoother connections between the outer layer and the inner layer as well. Okay, you can try this by essentially trying to balance things so that you get the first order derivative in here. But if we chose alpha equals 1/2, notice that at leading order, right, we would still have just the same equation that we had before, right, which is not going to provide us with anything new. So we need to bring these higher order derivatives into the problem, and the only way to do that is to set alpha equals to 1, right? You can't do it by setting, alpha equals to 0 or alpha equals to 1/2. Okay, so we're going to take alpha equals to 1, and that means that on the left we're going to have YL0 prime prime minus YL0 is equal to -1. Okay, XL is going to go from 0 to infinity, right, because it's this inner layer, and then we also have YL0 at 0 is equal to 2. Now we can solve this. We get YL0 of XL is equal to 1 plus A e to the minus XL plus 1 minus A e to the XL, right? Another thing to notice here, if we'd taken if we'd somehow taken a scaling such that we only got the first order derivative in here, then the problem would be that we wouldn't have a free coefficient to play with in order to do the matching. Okay, so getting your highest order derivative in here allows you to have more free coefficients in order to perform your matching. Okay, so just to shorthand the matching condition now, okay, rather than going through intermediate parameters, let's just look at the limit of YL0 as x goes to infinity, and the limit of our outer solution Y0 as x goes to 0. Okay, so if I look back here, right, remember my outer solution was just e to the x, right? So I get 1 on the right hand side. And here, if I take the limit as XL goes to 0, or sorry, as XL goes to infinity, I have that the only way to make this work, right, is if the coefficient of this is 0, right? So in order to get this 1 equal to 1 term here, I need to have this term vanish. And so I have to take A equals to 1 in this case, okay, in order to remove the blow up, okay, on the XL goes to infinity limit, okay? So I have now my inner solution on the left. I should be able to get my right-hand solution in a similar way. Let's take XR equals X minus 1 over epsilon to the beta, okay? I'm going to look at my expansion again, epsilon minus to the 2 minus 2 beta, d2yr over dxr squared plus 1 plus epsilon xr, epsilon to the 1 minus beta now, that's going to show up, dyr dxr minus yr is equal to minus e to the 1 plus epsilon beta xr. Okay. All right, so what's the distinguishing limit here? Okay, if I take beta equals 1, okay, then this term's going to be of order 1. This term's going to be of order 1, so I'm going to get to retain this, the 1 part of this term. This term's going to be of order 1, and the leading order expansion of the exponential is going to be of order 1, okay? So if I take beta equals 1, essentially I will retain the most terms in this case. And so that's our distinguishing limit in this case, okay? So at beta equals 1, we actually get this second order differential equation. yr0 prime prime plus yr0 prime minus yr0 equals minus e as xr spans between minus infinity and 0. Because remember, the right-hand side, right, we choose coordinates. I've chosen coordinates here so that I need, as x is going to be less than 1, right, this is all going to be negative values here, right? You can take a different scaling. So you can take the different convention if you want in order to make this positive, but the results are the same. So we also have a boundary condition, which is that at xr equals 0, right, we have 1. Because remember, in these compressed coordinates, when x is equal to 1, xr is going to equal 0. Okay. So I can solve this. I get yr0 is equal to e plus b e to the r plus xr, which I'll define, plus 1 minus e minus b e to the r minus xr. And these are just the eigenvalues of my linear operator, right? So 2r plus minus is equal to minus 1 plus or minus 5. We get the golden ratio in there for one of them, okay? And we require that yr minus infinity is equal to my outer solution at 1. And this, again, right, is going to, because this eigenvalue here is going to be negative, okay? As I take xr to minus infinity, this is going to blow up unless I take this whole thing to vanish. So that means that b equals 1 minus epsilon to prevent the blow up, right? And you'll notice, right, that it seems fortuitous that all I have to do is prevent this blow up, and maybe kind of by happenstance, right, I get the matching that I need along that boundary, right? So so that works out well, okay? But that's because we chose the right distinguishing limit. Okay? So the boundary layer on the right, okay, differs from the left because of the x coefficient we chose here, right? So now if we want to put this all together, okay, we can write that y is going to be approximated by y0 plus yl at xl minus yl at infinity plus yr of xr minus yr at minus infinity. Those are going to be the double counted terms. And we end up with e to the x plus e to the minus x over epsilon plus 1 minus e to the minus r plus 1 minus x over epsilon. Okay. And what we find is that our solution is going to look like this. So we have x equals 1 here, here's 2, and here's 1. And essentially, we have this sort of wavy shape to our solution, okay? And we get this nice smoothness. It's, you know, it's not too sharp. This is the case where I think this is, you know, like epsilon equals 0.1. I'm sort of drawing what you would find numerically. As you take epsilon to be smaller and smaller and smaller, you would squish this interior layer more and more against x equals 0 and x equals 1. And these transitions would be sharper and sharper and sharper, right? Because this exponential is going to fall off very rapidly the smaller you make epsilon, as is this one as x gets close to 0. Sorry, as x gets close to 1. Okay, so same ideas, not really a lot new in this example, but just showing that this works for two boundary layers. Okay, let me take a quick breath. Any questions about this? Okay, let's do a couple more and then we should be good for the day. Okay. Next example. Let's take a nonlinear system. Okay. Now notice that when we had that inhomogeneity, right, we Taylor expanded that. Okay. Same thing with nonlinearity. You can Taylor expand them, and then that, you know, each of those terms you attach to a different part of your hierarchy as you go from order 1 to order epsilon and so on. If I take the following differential equation, with boundaries given by y of 0 equals 0 and y of 1 equals 1, okay? Now we're starting to talk about equations that we couldn't just solve, you know, that easily by hand in full, right? So let's look at the middle solution to start. Okay, we'll sort of assume that we don't know if we can actually match the left and right boundary conditions with the middle solution. Okay, so if we set epsilon to 0, okay, then we just have this this equation. It's just a transcendental equation. E to the y0 is equal to 2 plus x, and we get that y0 is equal to log of 2 plus x. Okay, so then we're going to have this situation where we have x here's 1 and 0, okay? We have this log function here, and we need it to connect to 0 here, and it should connect to 1 here, I think. And there's no free constants in this, right? So we can't really satisfy any of these boundaries, okay? So we need the boundary layers to do that. So on the left, we'll use XL equals X, and I'll just jump ahead and say that what we end up getting is epsilon to the 1/2 as our distinguishing limit, if we sort of work through the logic as we have before. Y okay. So on the left, right, we have okay, good. All right, so we have YL prime prime minus e to the YL is equal to minus 2, and YL of 0 is equal to 0, okay? I can write this as 1/2 BD XL YL squared is equal to B minus 2 YL plus E to the YL, okay? And if we assume that YL goes to 0, okay, and YL of infinity goes to Y0 of 0 as YL goes to infinity, okay? Then what this implies is that B is equal to 2 log 2 minus 1, okay? So this implies that YL prime is equal to plus or minus the square root of 2 times B minus 2 YL plus E to the YL, okay? And we're going to take the positive since YL increases, okay? And so we just have an implicit solution in this case that XL is equal to the integral from 0 to YL ds divided by the square root of 2b minus 2s plus e to the s. Okay. Now, this implicit solution, right, it still has this this coefficient in it that we matched here, okay, using our boundary condition. So even though it's implicit, we can still pick up all the free coefficients. On the right, our derivation is similar, and we have xr equals x minus 1 epsilon to the 1/2. We get minus xr is equal to the integral from 1 up to yr ds divided by square root of 2a minus 3s plus e to the s. And we have that a is equal to 3, log 3 minus 1. Okay. Now to get our composite expansion, in this case, like in our previous problems, we just want to add together our outer solution, our inner solution, subtract off the contribution that's felt twice in our inner and outer solution. Okay, our right-hand solution, and then subtract off the value at our of our outer solution. And so we can write this just as log of 1/6 x plus 2 plus YL XL plus YR XL. Right? And so analytical solutions can be helpful even if you just have implicit ones, okay? Because these integrals, right, and then inversions are potentially easier to deal with than having to use like a shooting method or something like that in order to numerically solve the full differential equation. The other thing is you can get a sense of sort of the scaling of the boundary layers in the problem by sort of further analyzing these implicit solutions. Okay. So that's a nonlinear problem, right? As you can see, you end up sometimes with nonlinear differential equations that may not have explicit solutions, and you may have to work a bit in order to even get those implicit solutions. Okay. I have one more problem, but I think rather than rush through it, I'll save that one for Wednesday. So on Wednesday, I'm going to go through a chemical reaction system example, the case where you have multiple layers or exponentially small terms. And then we're going to start on interior layers and corner layers. And that'll probably take up most of the week. And I think by the end of the week, we may start to get into dealing with these matched expansions in the PDE, okay? So hopefully you see the kind of pattern in this approach that we used in the couple of examples that I've been through so far. You want to start by getting your outer solution, and that gives you some intuition on how to attack these inner solution problems. How many boundary layers do I need? Do I even have a boundary layer? All of these kinds of things come up by just doing sort of a standard starting regular perturbation expansion. And then some of the art of choosing your boundary layer can be to identify where the boundary layers actually are, but also in particular the small parameter scalings of those boundary layers. It's not always going to be the best choice to choose, x divided by epsilon for your boundary layer. You may get a different power, basically, of your order epsilon expansion there in the inner layer. Okay, so so that's it for today. Any questions before we conclude? All right. Well, good luck wrapping up the homework. I'll probably see some of you at office hours today. Yeah, otherwise I'll see you on Wednesday.
Hi. Office hours today is at 4, right?
That's right.
All right. Thank you. I talked to Dr. Mace and he gave me a paper, and I just wanted to double check with you that it's all good.
Oh yeah, sounds good. Yeah, happy to chat about that.
All right. Thank you.
Yep. See you later, soon.